Hi guys, welcome to this video on VLSI Career Point. In this video, I am going to talk about the VLSI industry from the perspective of India. So you might be hearing a lot of investments happening in the VLSI industry by the Indian government. You might have seen Ashwini Vaishnav, our minister, uh, promoting a lot of investments they are putting into a lot of companies. Now, I like to tell you much in detail what those investments are and where they are putting those investments and how can they affect you. And the target audience for this video is a student who is currently in electronics engineering in his BTech, or he's looking to pursue electronics engineering, he's in later part of his school, or an electronics engineer who just graduated and wants to look into career into the electronics industry. So this video is meant for you. Okay, so let's dive into it. So let me talk about the VLSI industry. So there are two parts. One of them is design. So this industry is divided into two major parts. One is VLSI design and one is VLSI manufacturing. Okay. Now, where Indian government is putting its money is majorly in this manufacturing part. So India, so what do we call the places or the factories where the VLSI chips or the semiconductor chips are made? They are called fabs, okay, or foundries. Okay, so India didn't have any decent foundry until now. So the government wants India to have its own semiconductor manufacturing or fabrication facility. So they are trying to put major of its money in this part. So you see developments such as Micron opening a plant in Gujarat. Okay, you see a Tata project coming again in Gujarat. Okay, so and there are different points. Okay, so who can target this manufacturing jobs? Obviously, electronic engineers and also the engineers who can handle plants. So we have chemical engineers, okay, we have mechanical engineers. So those kind of engineers and also electrical engineers. So those three branches of, and we need civil engineers to build those plants. So all this manufacturing will create a lot of jobs in India, okay. But right now, as I told you, I'm targeting the electronics engineering students here. So we can get into decent roles in this manufacturing industry as well. But the major amount or the 90% of market for you people is in VLSI design. Okay. Now, what is VLSI design? Basically, manufacturing is a very complex process. So the input to the manufacturing is a file which is created by these designers. Okay. Now, what is design? Uh, Now, what do we design? Like, what do VLSI engineers design? What are the end products? Okay, so they can be CPU, they can be GPUs, they can be your memory. Okay, so these are the major parts of your what do we design in the semiconductor or the VLSI design industry. Okay, so let me tell you what are the major CPU companies. Now I will tell you what is the market of these design engineers in India. So what are these CPU companies? You know Intel, you know AMD, you know ARM, okay, you know Qualcomm, you know MediaTek. So all these companies are there which have kind of are divided into the CPU industry. Now, Qualcomm and MediaTek, you might argue, are SoC companies. So what do they do is they take their architecture of the CPU from ARM and they put it inside the SoCs designed by their own teams. But Intel and AMD, they design their own CPUs, like proper CPU. Okay. And what about GPU? You know, the biggest player, uh, NVIDIA. Okay, so and memory, now you have Micron and you have Samsung. Samsung also designs its own CPUs, you know, Exynos series, right? So these are the major companies which work in the VLSI design domain. So these are the big companies, and we also have very, very great startups these days coming up from India or in India, having their design centers in India in the VLSI design industry. Now I'll tell you the major jobs in the VLSI industry in India. 90% of them exist in the design domain. Okay. Now let's break this design domain into different parts. So if I break this design, so we have firstly the field where I also work, which is the RTL design or the architecture design. Okay, these are not the same things, but they like stay like sit in the same or work in hand in this whole design flow of a semiconductor chip. So there's like RTL and architecture roles. So in this, what do? You define, you read the specs, you interact. So someone will interact with the customer, will tell you when my customer needs this much performance, he needs this much memory, he needs this much. This is the size of his device. So what I will do is, based on that, I'll design. You might have studied about logic gates in class 10th, right? So what does those logic gates do? They enable you to implement and or operations, and similarly you can like scale it up to even doing multiplication, division. Even today's GPUs, they do matrix inverse, and all those things they do in using this 1 0 or the logic gates. Okay, so what you will do is, you will design those, you will design the logic. So basically what you will do, you will use a language called Verilog. So this, I'm exclusively talking about RTL engineer. I am an RTL engineer, RTL design engineer. So we use a language called Verilog, or sometimes some companies might still use VHDL. So this Verilog is a programming language. It's looks like C, but it is not C, because the implication you get is real hardware out of it. Like if you write a C code, what you can do is you can compute an operation using that. Okay, you can implement a function using that. You can implement any mathematical operation using that. But in if you take the example of Verilog, so what will happen is, you whatever code you will write, it will implicate it into a hardware. It will implicate it when the end result you will see whatever code you wrote using Verilog. If you wrote, suppose let's take a basic example, if you wrote a code for an AND gate, right? So in so we have this AND gates. uh, you remember the sign of a symbol of an AND gate, right? So this kind of an AND gate can be implemented using your so this type of AND gate can be written using a Verilog language, and once it goes through the design cycle, it will be uh, at the end it will look like a combination of some CMOS transistors, right? So at the base of the chip there are hundreds and hundreds of CMOS transistors, and they act like switches, right? So they will act like switches. So basically it's a very complex, a chip is a very complex network of switches. Basically they are just switches. You have switches in your home, right? You press one, fan is on, you press it off, the fan is off, right? So those are transistors are, or the CMOS transistors are switches. So basically whatever logic you write, it is converted into switches at the end of this design cycle. Okay. So basically this RTL, so architecture engineer, what he will do, he will take the inputs from the customer, he will give the specifications to the RTL designer. This RTL designer will make the micro architecture of it. Basically the architecture will give me, okay, suppose here there is a block, it takes in data, it gives it some, if takes in X, it gives out in output it will give Y, right? So the work of an RTL engineer is to design the logic which will make this X into Y. Okay, so that is the role of this RTL engineer. If I go into the second part, so in the second part, if I go uh, second part after the RTL design stage is verification. Okay, so now whatever code I've written, now I told you the whole semiconductor chip is a huge complex network of switches. Now, I as an RTL engineer or someone as an RTL engineer can make mistakes, right? They can write wrong code, or basically whatever is implemented is wrong, right? The X is not giving Y. There can be some mistakes. So the verification team uses a very standard method of finding issues or bugs in the RTL. Okay, so whatever RTL or whatever logic I wrote, so this verification team will try to check it, okay, using a very standard uh, methods whatever they have. So they can, so now these days currently there are two major techniques of verifying this RTL logic or whatever logic the design team has done. So basically they are using a methodology called as universal verification methodology or UVM, or they are using these days Python using a extension or library called CocoaDB. So these are the skills, or these are the two major tools they use to verify. Now this Verilog code, now let's have a recap. So I got from customer, I got specs. Okay. Now those specifications go to the architecture team. Now this architect will make a diagram. Suppose an architecture, basically we relate architecture with a diagram, right? Whatever houses architecture will look like a diagram. This is the bedroom, this is the hall, this is, so basically it's such a complex that this chip with that specifications will have this block, that block, that block. So such a diagram we get from the architecture team. Now my RTL team will work on this architecture and implement it using a Verilog or a system Verilog, okay, or a UVM code. Okay, so now whatever this code I wrote, I will send it across to the verification team who will use UVM to, now I told you UVM or Python, so right now I'm taking example of UVM. So they will use UVM on this code, right? So maybe by mistake I told UVM here is what I can see. I don't know what I told. So VHDL code was there. Okay, I might have misspelled it as uh, UVM. So UVM is used by the verification team, and on this code base, on this logic, you can call it code, you can call it logic. Okay, so this code or logic, this team will use this UVM to find out bugs. Now, what is a bug? Any mistake as per, so verification team will independently read the spec or whatever this architecture document, the spec document, this verification team will read. So it will design its own test environment. It will design the sequences on which it will test this design. Suppose there is an operation, right? The architect told the RTL engineer that design an adder. Okay, now adder should do 1 plus 1 equal to 2. So simple test case of the verification time will be to give 1 and 1 as the two inputs of that adder, right? And they will put that my expected answer is 2. So they will match it, the output of this RTL, with 2, and if they get 2, they will tell the test passed. If they don't get 2, they will file a bug on the RTL team. So now you understand what is the, so this path is majorly called as the front end of the VLSI design cycle. Okay, so what we saw is the front end. Okay, let's move ahead. Now after this front end, what happens is, now you have, after verifying it completely, right? So there are three types of verification as well. So there's a formal verification, there is prototyping, emulations, a lot of things are there in between. I will not dive into them right now, but what they do is, now this verification can also have some, now you saw in the adder verification it was just mathematical, but what can happen is, I might have given a wrong reset condition, I might have given something wrong from the design part, but I'm still getting the correct answer in the functional verification. So what I told you was a function, like that block design has a function to add two numbers. Okay, now what I'm trying to tell you is there can be some other issues of that design, some other standards not followed or some issue. Right now I won't go deep into that, and I'll not confuse you with some wayward example. So what I'm trying to tell you, there are other types of verification, and also they try to run it on real hardware. Now you have a design, you will send it to the fab, it will get manufactured and will come back to you. But that's a long process. It's a costly process. You cannot let any bug go to that stage. Why? Because that will cause a lot of issues, that will cause a lot of financial issues, that will cause a lot of loss of money. Okay, so we don't do that. So what do? We have a lot of different types of verification before we send this design forward to a team called as physical design. I will go into physical design, but before that, all those different verifications, they will also map this RTL to something called an FPGA, field programmable gate array. So what is this? Just imagine you have a adder, right? So until your chip comes from the market, you don't have any comes from the manufacturer, you don't have any way to check it, right? On real sense, give the real voltage, probe it in your lab, you might have done it, right? So you don't have any option to check it. Okay, but you need to verify it right before sending, because that's a huge head of money which is going to be lost if you make a mistake. So you use the FPGAs, which are a programmable kind of hardware. Now you program, you write your Verilog code, and through the specialized FPGA software, you put that code there, and what it will do, FPGA is a kind of a chip, is kind of a board you get. In that board you connect wires, through that wires you put dump this Verilog code onto, there are gate arrays. Now all this I told you is lot of switches, hence lot of logic gates. So they have logic gates already implemented, so they will just map the logic gates there, and they will, as per the real values given on the inputs on the wires or through your software, they will check the output. So the real hardware test is done in this stage. Okay, so that is called as prototyping or emulation. So we call so emulation is kind of software based, prototyping is like on real hardware you do it. Okay, so these terms are there. So this is the middle part of the front end and the back end of the VLSI design cycle. Now we come to the back end, which is the physical design. So physical design uh, is a path in which we perform. Now we have the design, right? It's verified, it's tested on hardware, right? So you have the final design. Now what you will do, you need to map that chip onto your hardware. Now this is your silicon ka base, so on that you have to put your adder ka block somewhere here, right? Your adder block somewhere here. So you need to map it, you need to basically prepare the floor plan. Now an architect, if it designs a house, he has the floor plan, right, for a house. Similarly, you have a floor plan that my adder will sit here, the block giving input to adder will sit here, right? And basically this is if my chip is there, right? So here my adder is there. Okay, so the input, one input should be sitting here, other input should be sitting here. So what you do is you will place that circuits on the transistor level, right, in this physical design process. Okay, so this physical design is a series of steps lasting from routing, placement, floor planning. Okay, and so, and also these wires are there, right? So on this physical chip there are wires also going on, so your wires should not tangle with each other, right? So there are specific ways to route those wires as well. So that is the physical design of the backend stage. So there are specific tools. There's nothing now, there are millions of transistors, billions of transistors in a chip, so you cannot do it with hand, right? One block you keep here, one chip you keep here, you cannot do it. So there are softwares to do handle that. So you give specific inputs, there are tools, there is the language in which you communicate to the tool, you give the design, and the way you want to optimize, you will optimize using those software, and you will generate a GDS2 file. This GDS2 file, you give it, and that GDS2 file depends on the node or the process on which a chip is going to be made. Suppose it's going to be made in the 2 nanometer process, so that GDS2 file will also have inputs from those 2 nanometer. So now if I want, area is there where block is there in which area is a concern, so I'll try to use smaller switches there, so I can pack in more components, I can cover that whole component, right? Cover that whole block. Okay, so what I'm trying to tell you is, so that is also an input. So those things you pick up in a file and you send it to the manufacturing foundry, and that foundry will manufacture the chip for you, and it comes back to you. You have the post silicon validation teams. So India also houses post silicon validation. So you understand post silicon validation. So silicon comes. After that, you validate it, give in proper electrical inputs, and you look at the output and you figure out that yeah, my chip is working correctly or not. Okay, so that's the whole VLSI design cycle. I didn't cover manufacturing detail, but I did try to cover the VLSI design cycle. And now uh, I'll tell you, most of the jobs in India lie in the verification domain and the physical design domain. RTL design, there are less jobs, but there are jobs. But majorly, if you are a fresher, suppose you are a fresher from any NIT or IIT, you get into suppose AMD or Samsung. So they have the choice to tell you that you will work in verification or uh, you will work in the CPU design team, that is the RTL design team of designing the CPU, the GPU design team, that is the designing the GPU car logic, whatever logic I told, right? Or you will be in the physical design team, that is you will get the input from the designers, that is the RTL design team, and after going through thorough verification, and then you will implement the transistors or the logic on the chip, like how it will look, how exactly floor plan, how my chip should look, right? And there are a lot of teams now. If I come out of this unidirectional cycle, there are a lot of cross-functional teams who will also check the power requirements, they'll check the area, they will check the clocking, they'll check the reset. Now any digital circuit has a clock, has a sequential circuit has a clock and a reset, right? Through clocks the values they change in flip-flops, right? And also there is reset where you can reset the value. So those kind of teams are there, so different teams are there which do different work, but major field is RTL design, verification, physical design. So mostly you get jobs in India in verification and physical design in major companies. But if you go into a startup, like I worked in a startup for 1 year, so I had to do a lot of this whole design verification part by myself, right? So there are no boundaries, it depends on the role you get. But now uh, uh, so I would like to conclude this video that in India, the front end design or the VLSI design, front end plus back end in India has still a lot of scope. Okay, so now your next question will be how to get into this industry, how to get these jobs. So I will post a next video in which of this series in which I will tell you how to get into the jobs which I have or the roles which I have mentioned today, the front end, the back end, the emulation, prototyping part, power team, reset team, clocking team, CPU team, GPU team, how to get into that. So that thing I'll cover in the next video. Thank you for watching this video. Please like and subscribe, and please follow me on LinkedIn. What I have like I have given the link below. From that you will know who I am, what I do, why am I talking about this topic. You will get to know my background and all. So please do that, and please keep commenting. Please comment in this video and keep commenting and keep asking me questions. I'll try to post videos or give answers in the comments. Thank you for watching. Bye bye.